So today's lecture covers operating system for Internet of Things. We will focus on Contiki, an open source operating system for low power wireless IoT devices. We are also going to use Contiki extensively in this course. So we begin by asking, why do we need a separate operating system for Internet of Things? Internet of Things devices typically have very limited memory and they cannot run large operating systems such as Windows, Linux, or Macintosh. We are talking about memory and processing resources on IoT devices that can be orders of magnitude lower than that is required to run large operating systems such as Linux or Windows. Consequently, over the years, several different operating systems have been developed for Internet of Things, and these operating system includes like Tiny OS, Riot OS, Zephyr, and Contiki OS. We will use Contiki OS for assignments and projects in this course, and it requires minimal resources to run and has a wide array of support for networking and can across a number of different embedded platforms, including sensor tag that you are using in this course. And the best of all, this operating system is free under BSD license, and that means it allows you to use it for both commercial and non-commercial purposes. So Contiki OS is an open source operating system that runs on low power microcontroller and IoT devices, and it makes it possible to develop applications that make a very efficient use of the hardware while providing a standardized low power networking stack. So the Contiki operating system has its roots in Sweden, and it was started by Adam Dunkels, who after developing this operating system for more than a decade, as an academic project, spun out a company called ThinkSquare that continues to develop this operating system. And one of the core components of the Contiki operating system is something called ProtoThread. And this was also awarded the Test of Time Award at a major computing conference called ACM Census, recognizing its contribution to the field. The Contiki operating system is open source, and many companies and industries are developing this operating system today. This includes large companies such as Cisco, Atmel, and also universities like ETH Zurich and TU Munich. So Contiki OS has a modular architecture which is similar to the one that we show on the slide. It uses an event-driven mechanism at the kernel level and provides optional threading support for complex mechanisms. The Contiki operating system offers various services for IoT devices such as sensor data handling, communication, device drivers, and many other. And each of the service has its own interface and implementation. And the application only needs to know these service interface for it to make use of these services. So how small can an application with Contiki OS get? Typically, an application together with Contiki OS can be few kilobytes in size and use few hundred bytes of RAM. And this is really small. It is many orders of magnitude smaller than the operating systems that you use on your phone or your computer. So now let's look at the programming model and concurrency support, because it is one of the aspects that make Contiki really stand out, and it is extremely crucial for IoT devices to talk about concurrency support. So to just give an overview, we have different programming models to support concurrency on embedded systems. For example, in the sequential model, each task must complete before another task can be executed. For example, we might want to poll a sensor, process sensor data, and then look for if there is any packet received by the radio, and then receive information. And all of these steps are performed sequentially, where each of these steps is completed before the next task is performed. On the other hand, the event-driven model corresponds to external events and can support concurrency. For example, the CPU can switch to the radio to receive a packet and then switch to sensor to sample it to collect, for example, temperature reading. However, one thing that we should keep in mind is that event handler has to complete in an event-driven model. Finally, we have the multi-threaded model, which, like event-driven model, allows multiple tasks to execute concurrently. However, unlike the event-driven model, these tasks do not need to be run to completion and can be interleaved. For example, in the example shown on the slide, we process the sensor information, then switch to radio, and then we switch back to processing the sensor information, and then we switch back to the radio. So let's discuss the multi-threaded programming model. So this allows maximum concurrency, and in this model, the threads may be blocked while waiting for external events, such as, for example, sensor being triggered, or for example, sensor reading being available. And when the event occurs, the thread is unblocked and executed, and the thread can continue to run until it encounters another blocking event, or it is preemptive. That is, it is switched to another thread, as we show in the slide as well. However, one of the major downside of the threading model is that the RAM usage is typically not negligible, especially for IoT devices. As we show that for a node with 2 kilobytes, 100 byte is about 5%, and that could be the amount of memory that is required to support one thread. And why do the threads require this additional memory? It's to keep track of the state variables as you switch the thread, and to be able to restore back the execution to the point from which it was switched. So another programming model that is highly relevant for IoT devices is something called event-driven programming model. And in this model, the kernel switches to an external event handler when an event occurs. And these events can include, for example, receiving a packet through radio or completing the processing of sensor information. And when an event occurs, the kernel calls the relevant event handler, and then these event handlers run to completion, or within the event handler, we make an explicit return. And unlike threading, we cannot pause or switch to another event handler. And event-driven model have an advantage that they have very little memory overhead, making them an efficient choice for resource-constrained IoT and embedded systems. So what programming model does Contiki OS support? Contiki OS implements a hybrid programming model. It has an event-based kernel, and most programs run directly on top of the kernel. And the multi-threading is implemented as external library called proto-thread that can be called from the event handler. And these threads are typically only required when you want to perform long computation. Furthermore, Contiki also supports preemption. That means you can switch between the threads. And these design choices in terms of having this hybrid programming model allows Contiki OS to support threading while consuming as little memory as possible, which is important for IoT devices. So let's go beyond the concurrency. Memory management is another aspect where IoT operating systems can be different from conventional. So how does memory management in Contiki work? So in Contiki, there is no, for example, memory protection between application. And this can sort of like be a challenge from the security perspective. Contiki provides several functions, such as, for example, memalloc and memfree, that enables you to perform memory allocation and freeing. And these functions are specifically designed for constrained devices to be able to manage memory effectively on IoT devices. However, as we said, that there is no memory protection between applications. So one application can, in some respect, be, if it is mischievous, can cause corruption to another application. And it can also lead to issues such as memory leaks due to improper memory management. Finally, let's talk about communication protocol and support in Contiki OS. One of the key strengths of Contiki OS is the support for communication and networking stacks. And Contiki provides an implementation of a TCP/IP stack written in C. And in fact, it was one of the pioneering stack that demonstrated that TCP/IP could be supported on low power microcontrollers. Contiki OS also provides RIME, a lightweight protocol that supports primitives such as unicast and broadcast. And you are going to use this in one of the assignments as well as the project. In addition to RIME, Contiki also supports the latest generation of IP protocol called IPv6, and it allows these small, tiny IoT devices to be able to to connect to internet and have their own IP addresses. So how does a Contiki program looks like? So this is a very generic template for the Contiki program, and you need to define your own thread where you execute the code that you want to run. For example, if you want to just print out your name, you would need to include the file stdr.h, and you need to write a printf statement and the text that you want to print. and then you need to compile this and burn this code onto the IoT platform for it to execute. If you are going to run this code, it's going to print out hello world on the serial terminal. So of course, this is a very basic example, but you might want to do additional things, as we have also seen as assignment one, like toggle LED, or you might want to control sensor or buzz actuators. So, but the basic structure of the program would be something similar to the one that we show on the slide. So thank you very much.